Simplifying rational expressions means to get the expression down to its lowest terms. In simplifying rational numbers, we found that any number divided by itself is 1. So if we have factors in the numerator that are also in the denominator, we will cancel them out multiplicatively, which leaves just 1 as a factor, and 1 as a factor is an identity, so it doesn't change if there are any other factors still there. So recall simplifying a rational number such as 72 over 18. So we would completely factor the numbers. So any two factors of 72, that's 2 times 36. 36 is 6 times 6. And 6 is 2 times 3. So we're going to have 2 times 2 times 3 times 2 times 3. And the order of the factors doesn't matter because remember multiplication is commutative. Then we're going to find the prime factorization for 18. That's 2 times 9, and 9 is 3 times 3. So that leaves us factors 2 times 3 for our prime factors. And then any factors that are in the numerator that are also in the denominator, we cancel those out. So 2 divided by 2, that cancels. 3 divided by 3, 3 divided by 3. And so that leaves us in the numerator 2 times 2. And then in the denominator, there's no factors left. So that simplifies to 4. And we're going to simplify rational expressions the exact same way. And that is using a fundamental principle of rational expressions. For any rational expression, p over q, and any polynomial r, where r is not equal to 0, then p times r over q times r, we can separate that into p over q times r over r, which is going to cancel out those factors, leaving just p over q times 1, or p over q. So we can simplify that way. It shows us in order to simplify rational expressions, we must factor the numerator and denominator and then cancel, or in other words, divide any factors that are shared between them. Something important to remember as well is that canceling factors is not going to change the domain of any function. So you definitely would find the domain of a function before simplifying that function, because we're still going to exclude any factors that make the denominator equal to 0 before the simplification. So let's simplify some rational expressions here. Example A, we've got a monomial over a binomial here. So if you have a monomial, a single term, you can't really factor that according to the factoring flowchart, right? So that stays the same. But the denominator has 2 terms. So the first thing I'm going to do is lock them up into parentheses. And then I'm going to go through the flowchart. So there's 2 terms. Do they have a common factor? Let's see. It looks like they do. There's a GCF here of 3 for the numbers and y to the lowest exponent. So I'm going to factor that out, 3y cubed. Let's divide that from each of those terms to see what remains. So for the first term, that's going to leave 2y. And for the second term, those all cancel out, leaving 1 multiplicatively. And now that's completely factored because the exponent's 1. I know I'm done with the remaining polynomial. So let me divide any factors from the numerator that are also in the denominator. So 3y cubed. Okay, that's it. So what does that leave us in the denominator? 2y minus 1. And in the numerator, those divided, so that leaves just 1. You'll never have 0 from multiplication or division unless you start with 0. Okay. Then our next example, B, we have 3 terms in the numerator and 3 terms in the denominator. So I'm going to have to factor both of those. So let me start with the numerator. Is there a common factor for all of these terms? No. It's a trinomial, so that means we're going to have to unfoil this. So factors of the first term and the last term, such that the sum of the products of those factors is the middle term. So 5 is a prime number, and actually 1 is too. So let's see if we can make this work. If we multiply across, we've got the same sign, both negative. Yep, that works. So if you go across, we've got a 5x minus 1 factor in the numerator, and an x minus 1 factor. Okay. So let's look at the denominator. Is there a common factor for all of the terms? No. It's a trinomial. So let me see if we can unfoil this. Factors of the first and the last term. And we want to add up to the middle term. So 3 is a prime number, and so is 7. We just have to figure out which way it goes. It's probably not going to be 7 times 3 because that's 21. Too big. But if we multiply that across, 3x and 7x, different signs. Bigger is positive. That works. That adds up to 4x. So put the negative sign on that one, the positive on that one, and let's go across. So 3x plus 7 is a factor in the denominator, and x minus 1 is a factor in the denominator. So if there's a factor in the numerator that's also in the denominator, boom, cancel or divide it out. And let's see what's left. In the numerator, 5x minus 1. In the denominator, 3x plus 7. Remember, you can only cancel or divide factors, not terms. So this is as simple as that gets. For example C, we've got 2 terms in the numerator and 2 terms in the denominator. Lock them up in parentheses. And then let's see if we can factor them. So let's start with the numerator. Is there a common factor for both of these terms? Nope. They're the same sign. So are these perfect cubes? Yes, they are. If you take a cubed root of 27, that's 3. So this is x cubed plus 3 cubed. So that means that the numerator has 2 factors. The first factor is just x and 3. But the second factor is soap and boxes, right? So take 3 factors of each, box them up. So our first term is x times x, our second term is x times 3, and our last term is 3 times 3. And so the same sign as the original is a plus, opposite sign, and always positive. The denominator now, the variable has an exponent of 1, so I know that that's done factoring. I can't factor that any further. So let's divide factor in the numerator that's also in the denominator. And what does that leave us in the numerator? X squared minus 3x plus 9. In the denominator, you divide by 1. Guess what? You don't need to write that. It's understood. So this is as simple as that gets.